Hello, my name is John Ko, and I'm going to talk about encrypted cloud photo storage using Google Photos. This work was done while I was a PhD student at Columbia University with my advisors Jason Nee and Stephen Bellavin. Okay, let's get started. So we are producing more and more photos on a daily basis. Google Photos has over 1 billion users, and these users upload billions of photos on a daily basis. So how are we protecting these billions and billions of photos stored in the cloud? Well, normally they are protected using usernames, passwords, and two-factor authentication, which users provide to a login server, which then grants access to user photos. The problem here is that, well, first of all, attackers can try to guess, phish, or keylog these passwords or obtain them through password leaks. But not only that, the two-factor authentication is not enough anymore to protect against all kinds of adversaries. So here are just some examples of what I'm talking about. So in recent years, we've seen an increasing amount of incidences of rogue employees abusing their privileged access to their employer's servers to look at private user data for their own personal reasons. And last year, there was an interesting bug where Google Photos accidentally was sharing users' videos with random other users. So you might have logged into your Google Photos account and seen some videos appear in your account that did not belong to you, but belonged to some other users. And this very obviously is a compromise of user privacy. And they had nothing to do with usernames and passwords and two-factor authentication. So the big problem here overall is that a single compromise of your Google Photos account is enough to compromise all of your photos and data. And we are keeping more and more photos in services such as Google Photos. So the cost of one compromise is increasing. So what is a solution? Well, a solution is to have users encrypt their photos, but they don't. And there are two main reasons for this. The first is because encryption is hard because managing encryption keys is very difficult. The second problem is that if you encrypt your photos using a traditional encryption approach, they won't be compatible with services like Google Photos because Google Photos won't recognize them as image files. So the first point, encryption is hard because of key management. Well, managing encryption keys is very difficult. And at a high level, there are two kinds of crypto. The first is symmetric crypto and the second is asymmetric crypto. Symmetric crypto consists of using a high entropy symmetric key to encrypt your data and also decrypt it. The problem with this for users is that these symmetric keys are just way too long and complicated. So for example, a BitLocker recovery key, which is a 128-bit AES key, is this very long string of numbers that no user can memorize on a regular basis. The other option is asymmetric crypto, which uses private-public asymmetric key pairs. The problem with this is that users don't understand anything about public key cryptography, and this has been shown again and again in the literature and was especially shown in the famous Why Johnny Can't Encrypt paper. So basically, users cannot manage cryptographic keys. The second issue is that traditionally encrypted image files are not compatible with services like Google Photos. As you might know, cloud photo services do not allow uploads of files which are not images. So you cannot upload a text file and you cannot upload an audio file to Google Photos. What you can upload, of course, are JPEG images. But let's say you encrypt this image. It is now indistinguishable from random bits if you encrypted it using a traditional encryption approach. So Google Photos would reject it because it can't recognize it as a proper image file. So what we need is an encryption method which creates valid image files. The second issue of compatibility issues with Google Photos is that Google Photos will actually compress and slightly modify the photos which you upload to it. So you can imagine that when you upload a photo to Google Photos and you come back later to look at it again, Google Photos has actually compressed and slightly filtered it a bit. Now, this is a problem for encryption approaches. Let's assume that you've solved the first compatibility issue with Google Photos and have access to a format-preserving encryption approach. Now, if you upload the encrypted JPEG to Google Photos will perform a destructive operation on that image and compress it and might even filter it a bit. This is a problem because then if you try to decrypt decrypt that altered ciphertext, it won't decrypt correctly, and the resulting decrypted image will be corrupted and have artifacts, unless you design the ciphertext in a certain way. A third issue, which is left unaddressed by other work, is that encrypted images must be shareable with other trusted users, because users like to share their photos with others. So how can we share an encrypted photo with people that you trust without giving them access to your encryption keys? So there is indeed a large body of work which deals with image encryption. However, most of these approaches have problems. So they are generally incompatible with compression after encryption. If you upload their encrypted images to Google Photos and Google Photos compresses them and you download and decrypt those photos, they'll be corrupted. And most of these solutions try to maximize security and make these encrypted photos look indistinguishable from random bits, even if they preserve the format. But JPEG, as a lossy compressor, does not deal well with randomness. So the result are these giant images that are unusable. And finally, to get around these first two issues, some designs tried to create entire architectures from scratch to support their specific image format. However, this is undesirable because we don't want any modifications to Google Photos. We want users to just be able to download a solution which just works with existing services. So to address these issues, we propose a system called Easy Secure Photos, or ESP for short, which balances practicality and security. And it consists of an encryption algorithm and a key management solution. So the first part is the encryption algorithm. So on the left, we have the source JPEG and some secret seeds, which are used as the inputs to the encryption portion. In the encryption portion, we take the JPEG image, decode it, and split it into its 3 red, green, and blue color channels. And we apply a Fisher-Yates shuffle to each of these red, green, and blue color channels to encrypt each of them. These 3 color channels are then output as 3 separate grayscale JPEG images. And these grayscale JPEG images are basically the ciphertext of our encryption approach. And here's an example of what it looks like. On the left, we have a photo of a very nice kangaroo, and on the right are the ciphertext images which result from encrypting this kangaroo photo using our approach. So outputting 3 separate files, 1 for each color channel, is very important for our approach and is the reason why it's robust against compression of ciphertext, has a negligible effect on quality, and retains the JPEG format so that it's compatible with existing services such as Google Photos, Imager, and Flickr, and more. Since we're using JPEG photos, it doesn't matter what service you want to use. You can, as long as they upload or as long as they accept JPEG images. So why does it work? This unfortunately requires a technical understanding of the JPEG format, which is beyond the scope of this very brief 15-minute talk. If you'd like to learn more about how it works with the nitty-gritty details, please see the paper, or please feel free to reach out to me with any questions you may have. What I would like to focus on are the secret seeds, which are used in the encryption. So the secret seeds are 384 bits each, and there's 1 for each color channel. These secret seeds are unique per image, and they're stored in the metadata, and they're used to drive the Fisher-Yates shuffles for our encryption. Now these secret seeds, since they're stored with each image, they need to be protected as well. So we encrypt the secret seeds using the public keys of our image-based key management approach, or IKM for short. So why do we need IKM? Well, the problem is users can't manage cryptographic keys, and it gets even worse when they have multiple devices, because when a user has multiple devices and that user is using encryption, they need to be able to encrypt and decrypt their data on all of their devices, not just one of their devices. So normally what will happen is that a user will have to synchronize their private key or their secret key among all of their devices. However, this is inadvisable according to security best practices. People don't know how to move their keys around, and they don't even know the first thing about key management in general. So IKM's approach is, let's keep the encryption keys on each device so that they don't need to be moved around. And instead of showing users the idea of key management, let's instead show them device management, because users much better understand how to manage their devices. They know how to synchronize and pair their devices with each other, and they don't know how to manage secret cryptographic keys. So that's the basis of IKM. So with IKM, each device on the left here has its own key pair, its own private public key pair. And every device uses its public key to encrypt an AES key. This encrypted AES key is stored in Google Photos. And this AES key is used to encrypt and decrypt the secret seeds which are stored with each image. And then those secret seeds are used to encrypt the JPEG images themselves. So of course, if you want to decrypt an image, you need to have access to the AES key, and then which can be used to decrypt the secret seeds, which then are used to decrypt the JPEG images. So this is a key encrypting key scheme. So the problem here is that if you want to be able to encrypt your photos on one device, but have all your other devices be able to decrypt those photos, they need to know each other's public keys, because then if one device, or rather if all devices know every other device's public key, then any device can encrypt a photo and make that photo decryptable by any other device. So we need to have this ecosystem, this web of trust among a user's devices, so that they all trust the public keys belonging to each of their devices, or each of the other devices. So we guarantee this using a secure pairing approach augmented by a password authenticated key exchange to build trust, like a web of trust among a user's devices. And the details of this are in the paper, of course. Now, in order to pair devices and exchange their public keys, they need to have some kind of communication channel available, but there is none here. There's no text-based communication channel available. And we don't want to rely on a third-party service, but we would like to have some platform-independent mechanism. So let's just use the photo hosting service itself as the communication channel. So what we do is we encode IKM encrypted protocol messages in QR codes, and these QR codes are saved as images which are uploaded to the photo service. So every device has access to the photo service and the user's account, and can see these QR code images uploaded by other devices and communicate with them this way. And QR codes are nice because they're robust against compression and modifications. So Easy Secure Photos encrypts photos with secret seeds before uploading them to services like Google Photos. And then IKM takes care of synchronizing public keys among users' devices in a way that allows each device to encrypt and decrypt any of a user's photos. But at the same time, users don't actually know what's going on with the key management. What they see instead is device management. So what the users see is that they are synchronizing and pairing their devices with each other. They're not worrying about key management. So we implemented this by modifying a popular Android app called Simple Gallery. It has millions of users. And we also supported IKM by modifying Open Keychain. To show IKM is easy to use and understand, we conducted a user study to evaluate its usability according to the system usability scale. We compared the results against our previous work involving PGP and E3. PGP stands for Pretty Good Privacy and is the gold standard for secure email, but also represents highly unusable traditional cryptographic key management abstractions. E3 stands for Easy Email Encryption, which is a previous work of ours, which explores secure email with device management abstractions to make it more usable for users, while ESP is Easy Secure Photos, of course. E3 and ESP both use device management abstractions for its key management, and this shows in the system usability scale scores, which are above 70, which is good. PGP, on the other hand, has a system usability scale score of 40, which is well below 50. Anything below 50 is considered unacceptable. So essentially, our device management abstraction strategy for key management is considered intuitive and usable by real users who use our system. To conclude, I'd just like to highlight the fact that even though this talk and the paper focus on Google Photos, Easy Secure Photos in fact works with other photo services as well. It is not just limited to Google Photos, but is compatible with Flickr, Imager, and more. So I'd like to thank you for your time, and if you have any questions, please feel free to reach out to me, or please just take a look at the paper. Thank you.